Yeah, please go ahead
All right.
whenever you like.
All right. Yeah, thank you. Yeah, so thanks to the organizers for asking me to talk about repeating FRBs. I apologize that I can't be there in person, that I wasn't able to travel for a number of reasons. So I understood the request as to give an overview of repeating FRBs. There have already been a number of talks on repeaters, so I hope I can skip through some slides quite quickly. But let's, of course, begin with the obvious, which is what is a repeater. So a repeater we generally define as a source if there are two or more bursts originating from a consistent position on the sky, and these bursts have a consistent dispersion measure, at least on short timescales. So if those two criteria are met, we consider the source to be a repeater. So currently, at least according to the FRB newsletter, there are 58 confirmed repeaters. The overwhelming majority have been discovered by the CHIME FRB collaboration, which is a survey, of course, operating on the CHIME telescope, and I've showed a picture here on the right. And then there's been a handful that have been discovered by additional telescopes, such as Arecibo, FAST, ASCAP, and DSA, and I apologize if I've forgotten any. CHIME FRB does a very careful analysis, and in their observing band of 400, 800 megahertz, they have about 3% of their sources are confirmed to be repeaters. And so even from the very early days after finding the first repeater, there was a lot of discussion about whether this repetition versus non-repetition actually reflects something distinct about the populations, meaning that are there two different types of FRBs, some repeat and some don't? And this is a discussion that remains, that happens at essentially every meeting, even up till now. So of course, one can ask oneself, are there observational difference between these two? And again, I'm going to go to CHIME because they just have such a large number of bursts and great statistics. And a paper that Ziggy Plenos put out a couple of years ago using the Catalog 1 sample is that repeaters tend to have band-limited emission, and they tend to have longer durations and time, whereas the apparent one-offs tend to be broader band, so emitted or observed over the full CHIME band, as well as having shorter durations. And it's my understanding that the analysis from the Catalog 2 supports these broad statements. Although there's some really nice work by Alice Curtin that shows some subtleties to this interpretation, but I don't have time to go into that right now. So another feature which is common, if not ubiquitous, among repeaters is that we see complex spectral temporal structure, meaning that you see bursts would have multiple components in time, and often these components actually drift downward in frequency to later times. So here I've shown two examples. These are actually from the GMRT, from the FRB 2018-09-16B. And in this observation, what we did, we broke the GMRT into two subarrays and observed in band 4 and band 5 simultaneously. And we caught these two bursts in both bands, or this is the only two bursts that we had where we saw in both bands simultaneously. On the right, what we think is it's actually a continuation of this sort of sad trombone effect from band 5 through the gap and then down into band 4. We caught the edge before it disappeared below our sensitivity. And in left, we actually have a very unusual case where it seems that you have sort of a burst at the top, and then you really do have a gap, and then a simultaneous burst at lower frequencies. To the best of my knowledge, this is the only time this happens. Generally speaking, if we have emission, it's really restricted to a single isolated island of emission. And one final statement about the population is that, we can broadly classify repeaters into sort of stormy, sometimes people say hyperactive sources, and calm sources. So what this plot on the right shows is data from the public CHIME FRB repeater catalog, and it's just the arrival time in MJD of a burst, and I've stacked all the sources according to their discovery date. From earliest to late at the bottom and earlier detections at the bottom and recent detections at the top. And you can broadly see sort of two features. For the most sources, you really only have a handful of detections. Then there are a couple of examples, which I've highlighted in sort of solid boxes, where you see many sources, many bursts, often for some period of time, and then they shut off. Sort of very clearest example is perhaps the sort of light bluish up towards the top, 2022-09-12A. But for the most, you really do have only a handful of bursts. And the other thing I want to mention is that this activity, this property of repeaters is also frequency dependent. So to give an example, again, if you look at the cyan, the sort of light-colored blue at the top from 2022 0912A, you see that CHIME detected many, many bursts over these course of whatever 500 days. And similarly, FAST, which did a lot of monitoring of the source, saw also many, many bursts. They had a peak detection rate of 390 bursts per hour. But then if you contrast this with a source which is talked about a lot this meeting, 2024-0114A, which is one line above on this plot in sort of the medium blue with a dashed box around it, CHIME has only detected sort of a handful, I think 5 bursts, whereas FAST has seen detection rates as high as 730 bursts an hour and have something like 1,000, at least 1,000 detections. And right, it's the same telescope, sensitivity hasn't changed, but so it's also clear that this stormy and calm behavior is also, to some extent, frequency dependent. And my last note on this slide is that a lot of our observational data is biased towards these stormy, hyperactive sources because you can get a lot of bursts, so everyone gets really excited about it. But it's actually not clear, of course, how reflective they are as a population of a whole. It's unclear whether these less active sources are just less active versions or whether there's something fundamentally different about them. So this is my one and only theory slide because I'm not a theoretician. I just wanted to mention that most of the models that try to explain repeating FRBs do invoke a neutron star. Broadly speaking, there are 2 scenarios. There's the nearby emission scenario in which the bursts are originating in the magnetosphere of the neutron star. And the other class of models is sort of the far away in which the bursts arrive in the surrounding material caused by shocks due to some activity in the magnetosphere. But there are experts there who can describe this in more detail. So I just wanted to mention it very briefly. So one of the advantages of repeaters is they allow a wide range of follow-up observations. And I have highlighted here, broadly speaking, 3 motivations for why you'd want to do follow-up observations of repeaters. The first is to localize post-discovery. So if you discover a repeater, but you don't have sufficient localization to assign it to a host galaxy, you have the advantage that you have you have time to keep trying and hope that you finally are able to localize. This motivation, I would say, is largely now unimportant now that CHIME has their outriggers and can do their own localization and even really precise localization. So I don't think this is going to be a major motivation, certainly not in the Northern Hemisphere. What is still highly important, though, is looking for high energy counterpart searches. So looking for example, bursty X-ray emission that may or may not be coincident with a radio burst. The only simultaneous radio X-ray or radio high energy detection we have, of course, is the source in our from the magnetar 1935 in our own galaxy. We have not successfully done this for an extragalactic source. And of course, the ones that are nearby are the ones that are more interesting because they provide the deepest constraints. And then the third motivation is the one that I'm going to focus on for the rest of the talk, and that is doing searches for additional bursts in the radio in order to build up statistics and do a wide range of physics with it. So specifically, I'm going to focus on 3 analyses that can be done because I could talk for hours and hours if I went through all of them. First one is polarization. Second one is high frequency emission, and the third is the wait time distribution. So thankfully, I don't have to go into a lot of detail because before lunch, Manisha gave a great overview on this. I just wanted to briefly remind everyone that we have 2 active repeaters that show very, very stable position angles, both within bursts and between bursts on time scale of hours. I've given an example here from the GMRT, which is the 2028-0916B. And we then have 2 examples of repeaters that show polarization position angle jumps on very short time scales, certainly between bursts, but even on time scales, or even interbursts. And this is what Manisha presented for, sorry, I forgot to put the name, 2024-0114A. And the question that I want to throw out again is, I'd love to get feedback from the theorists in the audience on what could the role of plasma propagation? Is it possible that these jumps are due to, superposition of various plasma emission mode or propagation modes, or is it more likely that this really does reflect changes in the magnetic geometry of the source on these timescales? But certainly for the cases where, I think in general, but also in particular for the cases where the PPA is very steady, I think combining that observation with the lack of any short-term periodicity, which might be associated with like a typical pulsar or neutron star rotation period of, say, less than tens of seconds, which has never been found despite many, many searches. I think this actually provides two very interesting constraints. In fact, I think it's getting potentially difficult to reconcile both the steady PA and the sort of magnetospheric models. So I'd also love to hear feedback from the theorists on this point. So I'm going to move on to my second point, which is the detection of high frequency emission. So several years ago, the very first repeater, 121102, was detected up to 8 gigahertz with the Green Bank telescope. This is the highest frequency detection of a repeater or any FRB, to my knowledge, to date. And I'm very happy to report that actually with Effelsberg, we were able to also detect 2024-0114A up to 8 gigahertz using our CX receiver, which operates from 4 to 8 gigahertz. And this is work done by Simone Meschia, who is an Erasmus intern working for me over the summer in Bonn, and he's gone back to Italy now to finish his master's. So now we have two sources which have repeating FRBs, which have detections up to around 8 gigahertz. And for the rest of the talk, I'm going to focus now on the wait time distribution, and I'm going to discuss primarily data from the new UBB receiver. This is the receiver that Anissa also mentioned this morning, but to remind you all, UBB stands for ultra broadband. It has an instantaneous bandwidth of 1.3 to 6 gigahertz. Note in this plot on the right, I've shown a single pulse from the Magnetar 1810. This was taken with our older hardware setup, in which there was a gap between 2.6 and 3 gigahertz. This is now no longer the case. We now have truly simultaneous coverage from 1.3 to 6 with no gaps, but this is still the most beautiful dynamic spectrum I have from with this repeater or from this receiver, and so I chose to show it. This receiver is complemented with a very flexible backend called the EDD, which allows a lot of user configurable time and frequency resolution. And the main point, additional point I want to get across today is that this wider bandwidth significantly increases your chances of detecting a repeater. And this is not just because having a wider band allows you to reduce the radiometer noise. You really just increase the chances that you happen to catch a burst. And I have that illustrated here. So these three bands show the three frequency ranges of our, so we'll say legacy or previous receivers. So we could have basically observe in one of these three bands. And what that means is, let's say you're observing this repeater, 2018-0916B, you would have, if you were observing with our standard L band, detected this burst, but not the others. Or if you were observing with our CX receiver, you would have detected this one, but not the others. And you never would have detected this one because we didn't have that coverage. Now with the UBB, you get all three bursts in one observation, and thereby, and this is the way that you actually quite rapidly increase your chances of detection. I also want to highlight that this green band at the bottom sort of gives a notional 300 megahertz bandwidth that's typical for a lot of the surveys that are going on, like ASCAP or DSA 110. And just to point out that the burst on the left would have covered the majority of this band. Therefore, we would have said, okay, it's sort of a wide band burst that sort of goes off the edge of the band, but we don't really know how far it extends. And now with this wide observing band, this burst is no longer a wide band. This burst is actually a very narrow band, and we know exactly where it stops and where it starts. So, of course, we observed this hyperactive source, 2024-0114A. We have over 700 bursts detected with this receiver in 4 epochs. This is also the burst, the data that Manisha mentioned earlier. So one of the epochs is illustrated on the right. Here we have the frequency versus time since the start of observation, and each burst is illustrated as like a vertical bar, indicating its emission bandwidth. And you can see a couple of features. One, not a single burst is observed across the entire band. Of the 700 bursts, not a single one. In fact, the broadest burst is about 1 gigahertz. You also see there are more bursts at the bottom of the band than at the top, which is perhaps not surprising. But also if you look at not the actual emission bandwidth, but the fractional band, so the emission band divided by the center frequency of that burst, we see that it's on a statistical average, it's very consistent with being 0.1 across all of the frequencies. So now I want to finish up by talking about the wait time distribution. In here, again, the wait time distribution is essentially you just line up your burst in time and you calculate the arrival time between, say, burst 2 and burst 1, and burst 3 and burst 2, etc. So I have this little cartoon with the yellow circles indicating sort of time and then the separation. And what we also universally see in all repeaters is 2 time scales. So we have a longer time scale, which is greater than about a second, and then we have a shorter time scale. So the longer time scale, you can demonstrate quite clearly, we've done this for a number of sources, that this distribution is dictated by a Poisson statistics. And within an observation of a couple hours, all of the bursts do follow Poisson arrival times. And so in this distribution, you expect the histogram to be exponential. And then if you combine multiple observations together, then you have a sort of a stack of multiple different exponentials with slightly different rates. And that's what's then shown on the right. In the literature, this is fit by a power law, and I would argue there's actually no physical motivation for doing this. The physical underlying process is actually a stacked exponential due to Poisson statistics. So on the right short time scale, you can see again, 2 things. One is that in this particular analysis, which was done by Yosha, who actually just spoke before me, he separated the time, so he indicated a difference between separate bursts shown in blue and subbursts of a single burst shown in orange. And you can clearly see that there's a continuum. And I think there was a question this morning asking whether this is a sensitivity effect, meaning if you had more sensitivity, would you in fact see bursts which are in our data, separate turn into subbursts of a longer burst envelope? And I think the answer to that is yes. It's almost certainly the case that this distinction is on some level sensitivity. But also note that the time scale does not change with the Poisson rate. Where on the right, you can see how the burst dots sort of move slightly to the right or to the left, depending on what the rate is in that particular observation, but the left clusters are actually fixed. So this, I would argue, is the left time scale is telling you something about the characteristic time of an emission mechanism, so the characteristic duration of an event. Whatever an event is I think what is being highlighted here. And so now we're going to shift to 2024-0114A with the UBB. So what we did is we basically assigned every burst that we detect, we assign to one subband, which we call 1 through 6. And then we do statistics of the bursts in that subband. So on the right is the wait time distribution from RB2, which is from 2 to 2.6 gigahertz roughly. And again, you see sort of, broadly speaking, 2 clusters. You have the Poisson at the right, which is consistent with the exponential. And then on the left, you have the clustered, again, the interbursts and the subbursts are a continuum, suggesting that this is just a sensitivity effect. But you can also see that there isn't an obvious gap. And in fact, if you look at the fast data, where there are tens of thousands of bursts, you very clearly see that there's no gap between the short time scales and the long time scales, meaning that the clustering time scale and the Poisson time scale merge at some point, which could be, so whatever the event is, it has some time scale of tens of milliseconds. And this source is so active that the next independently emitted burst is starting before the previous one ends. So that's sort of one interpretation of this. And I think this is interesting both from a theory standpoint, that I think in addition to sort of the millisecond time scale as being sort of a fundamental time scale of the process, I think that this duration of sort of 100 milliseconds is also an important fundamental time scale that should be considered. So now I want to go in, like I said, we have this beautiful wideband receiver. So now we're going to look at the wait time, also taking into account the spectral information. So here at the top, I have another cartoon where we have 3 bands, and now we have 3 arrival times, time series in each of the 3 bands separately. And now instead of asking what is the time difference between instead of just asking the question, what is the difference in time between 2 consecutive bursts, we also ask the question, what is the difference in band? So for example, my cartoon on the first 2 bursts are both in band 1. So there they have a band difference of 0. but the next two, between burst 3 and 2, burst 3 is in band 3, burst 2 is in band 1. So there, the band difference is 2. So positive 2. So differences that go upward in frequency are positive, and those that go downward are negative. So I hope that makes sense. So now what we do is we calculate those differences in time and in bands, and we plot it on the left here as a band difference versus waiting time as a heat map. And again, you see two broad features. You see a right cluster of events at timescales longer than about a second, and then you see a cluster of shorter timescales. And the key feature of the longer timescale cluster is that it's symmetric, and there's no obvious grouping somewhere away from it's symmetric is I think the easiest way to interpret it. So you can see this more clearly if you look at the histogram at the right, where Pranav has basically collapsed the waiting times longer than a second. It's shown in blue. And to within the counting errors of each bin, you see that there's equal numbers of positive and negative. There's equal numbers of differences of +1 and -1 and +2 and -2. So therefore, this independence in time at a given frequency holds over multiple frequencies. In other words, the events which are dictated by Poisson statistic, meaning that they are independent, are not only independent in time at a given frequency, they're also independent in frequency. So the emission at one frequency on longer time scales does not predict the emission at some other frequency. This is different in the other cluster. Here we see, if you look at timescales less than a second, that actually there's a preference for a band difference of -1. And this is likely sort of the sad trombone effect, right? There's this drifting structure in some subbursts where you see it go down in frequency to later times. There are a few cases of upward trombones, so happy trombones. Those are these two sort of at a band difference of +1, but the majority are a negative band differences. And really a band difference is sort of -1 or -2. But this difference actually goes beyond just sort of the tens of milliseconds scale you see typically in a single burst, but actually extends over the entire clustering time scale of sort of 100 milliseconds. So in this time scale, we do actually see preference that if you see a burst at a given frequency, it's more likely that the next burst will occur at a lower frequency. And that is also illustrated on the histogram on the right in the yellow, where you see that there's actually a slight shift in the peak to around a band difference of about -1. Anyway, I hope that makes sense. This plot I know is a little bit confusing. Yeah, so I'm going to conclude now. Basically, repeaters are a subclass of FRBs, which enable a wide range of follow-up studies. And I think the polarization of active repeaters suggests that either there are two populations or something, or there's something geometrically different about the two populations, or propagation effects are playing a key role, and there might actually, in fact, be one. Two repeaters have now been detected up to 8 gigahertz. And I think, as I said, the spectral wait time shows that this distinction between the independent and clustered events extends over at least the sort of most of the gigahertz radio spectrum. And so with that, I'm happy to take questions.
Thank you, Laura. Questions, comments?